Hello, this is Mr. Huebner, and in this video we're going to be talking about NMR, specifically HNMR, which stands for Hydrogen Nuclear Magnetic Resonance. So we'll just write that down. Got HNMR is nuclear magnetic resonance. And it basically summarizes the whole idea of what we're doing. We're dealing with the nucleus, and it's putting a nucleus in between two magnets, and essentially it's reversing the spin. It's going one way, and when you put it through a magnet during a specific frequency, radio frequency, it'll flip it, and the nucleus will spin the opposite direction, and that can be recorded electronically in the form of a spectrum, and that's what we're going to be analyzing. IB's not too concerned with the theory, but they do want you to know how to interpret the NMR spectra data. So this only works when the nucleus has an odd number of protons, like with hydrogen has 1. You have carbon-13, NMR, which has 13 protons. You've got fluorine-19, and then also phosphorus-31, and there's more. These are the common ones, HNMR being the most common one. So I'm just going to pause it and draw a picture real quick. Alright, so here's a little picture of the proton that is found between these two magnets. It's put into this, basically an MRI, magnetic resonance imaging device. NMR is the same thing, just with a different name. They call an MRI an MRI because it doesn't have the word nuclear, so it's less sound safer. So right here we got the spin, and under the right frequency of the radio waves, it will flip within those magnets and start spinning the other direction, and that can be detected in the spectra. So we got nuclear magnetic resonance. We got nuclear, the nucleus. We got magnetic, putting it into a magnet, and we got resonance. So once radio waves have the exact frequency needed to make the nuclei flip over and spin in opposite direction, that can be detected electronically in the form of a spectrum. This is what is called resonance, that flip with the right radio frequency. Alright, so that takes us to this page right here, and this is in your packet. What we have to do is identify the different types of hydrogens that are present. So now below here, let me zoom up on this. This is your typical spectra data for NMR. You have, here's what's called the triplet because there's 3 little peaks. This is called a doublet because there's 2. If you had just 1 peak, it would be called a singlet. And here, this is called a multiplet because there's 4 or more, or you could call this a quartet because there's 4. Alright, so each of these peaks represents a different type of hydrogen. So if we move up here, this hydrogen is connected to a carbon that's connected to 2 hydrogens and a chlorine. This hydrogen is connected to a carbon that's connected to 2 hydrogens and a chlorine. These 2 hydrogens are identical, at least chemical shift-wise, in terms of the radio frequency of the nuclear flip within a magnet. So both of those are going to be represented by 1 peak. However, this hydrogen right here is connected to a carbon that's connected to 1 hydrogen and 2 chlorines. That's different than these. So really, we have 1 and 2 different peaks that would be shown if this molecule were to be put through an NMR device. Here, on this other question, we have a H that's connected to a carbon that's connected to 2 chlorines. These H's are connected to a carbon that's connected to 0 chlorines. So these are 2 different hydrogens, they're going to be two different peaks, because each of these hydrogens is similar, the same pretty much. Let's fill this one out. H's. Now this hydrogen is connected to carbon that's connected to three hydrogens, and same with all of these hydrogens. So these are all the same because of symmetry, but then these hydrogens are connected to carbon that's connected to just two hydrogens. So these are a different type. So again, we're going to have just two peaks. Alright, looking at this one, you've got this hydrogen's connected to a carbon that's connected to three hydrogens. These hydrogens are connected to a carbon that's connected to three hydrogens. So really, they're the same thing. So you are only going to have one peak. Alright, so this would be a good time for you to work on the rest of them. I'm going to pause the video and work on them myself, so this would be a good time to pause the video as well. Alright, here are the answers. We have these hydrogens, due to symmetry, are the same. These are different. Here, because of symmetry, all of these hydrogens are the same except for this one that's off of the center carbon. It's different. This is a little bit tricky. You might not have gotten this, but we have to look at the electronegative entity, and that's going to create a chemical shift and draw electrons towards itself, which is going to cause each of the hydrogens as you go further from that chlorine to be different. So these are both equidistant from the chlorine, so they're the same. These are a little bit different, and this is different still. Because if you look at it, it's a hydrogen that's attached to a carbon that's significantly far from the chlorine, but both these hydrogens are both attached to carbons that are a little bit closer to chlorine, so they are a little bit different. And here, we got 1 and 2. Alright, moving on, I want to talk about neighbors. So this was just talking about how many different peaks are there, but now we want to figure out, are they going to be singlets, doublets, triplets, quartets, or multiplets? And the rule of thumb is peaks minus 1 equals neighbors. And we got to figure out, alright, what is a neighbor? If we look at this, a neighbor hydrogen is a hydrogen that's hanging off of a carbon next door. So this hydrogen is connected to a carbon that has two of its carbon neighbors. Their hydrogens are next door. So here's our house, there's next door on either side. So this hydrogen has 1, 2 neighbors. So you could reverse this and do neighbors equals, or neighbors plus 1 equals peaks. So if you have 2 neighbors, that's really going to be a triplet. This is going to have 1, 2. Yeah, so this is going to have 2 neighbors, so it's going to be a triplet, whereas this one's going to have 2 neighbors, so it's going to be a triplet. But whenever you have a benzene ring, they're going to be lumped together kind of down here on the graph. And so sometimes it'll be so tight that you can't really see the difference between the 2 triplets. It'll look like a blur. IB is not going to be asking you about benzene rings. It's a little bit more advanced, and high schools don't have the NMR equipment to be able to explore in that depth. So, looking at this, we have a triplet, so 3 peaks minus 1 is 2 neighbors. So I'm going to write 2 neighbors. And each of these peaks are going to represent these different hydrogens in this molecule. So here we got 2 peaks minus 1 equals 1 neighbor. So now we got to determine, is this peak 1 or is this peak 1? So these 2 hydrogens here have 1 hydrogen neighbor. So that would suggest that this peak is being represented by these hydrogens. So these are peak 2. 1 neighbor, therefore a doublet. This hydrogen right here has 2 neighbors, so it's going to be a triplet. And so that's peak 1 that triplet with 2 neighbors. Alright, we're going to do this bottom one right here. H, 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 H. Oops. We don't necessarily put them all H's. We might need to put some sort of halogen. I'm just going to use chlorine as an example, like the above question. Here we got a quartet, and there we have a doublet. So there are 2 peaks. 2 minus 1 is 1 neighbor. Here we got 4 peaks. 4 minus 1 is 3 neighbors. So let's just put a chlorine right here. This chlorine, or these hydrogens right here, have 1, 2, 3 neighbors, which looks like it would be represented by the quartet. And, alright, this is 1 neighbor, so that would suggest that this needs to be a chlorine, and this needs to be a chlorine as well. Wait. No, we can't do that because that changes everything. So this is a H, and this is an H, alright, because these are the 3 neighbors. But we can change this. So we're going to have to get rid of that and put a Cl. There we go. So it's H, 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 Cl, H, Cl. Because this one has 3 neighbors, and these have 1 neighbor, and that's represented by the doublet. So you can see it can get a little tricky. This is, getting at the basics, and they get to be more complex, the molecules. But IB is going to be focusing on the basic ones as well. All right, next, what we're going to do is talk about shielding and upfield versus downfield. So, I think this is recording my screen. Hopefully it is. We got downfield it's kind of counterintuitive. Like as the numbers go up, it's going downfield. As the numbers go down, we call that upfield. So kind of zeros like top of the hill, upfield, and then you go downfield. And downfield is going to be a de-shielded proton, and upfield is going to be a shielded proton, and the shield is going to be made of electrons, essentially. So, look, it has to do with the electronegativity of a specific atom that is present. Typically, a halogen is going to be the common example that's going to be used at this level. Or it could be an OH, or an NH2, some organic functional groups. So, those NH3s, the OH, the halogens, those are very electronegative. So they're going to draw electrons towards themselves, therefore de-shielding that hydrogen proton. If the entity is not very electronegative, those electrons around the hydrogen proton aren't going to be pulled away, and therefore we're going to call that shielded. So right up here is shielded, where electrons are not pulled away. The entity next to that carbon that has a hydrogen attached to it is not very electronegative. But the more electronegative the entity, the more downfield it'll go, because it'll de-shield those hydrogen protons. And that's upfield, downfield, de-shielding, shielding in a nutshell. So why don't we do a simple problem? Let's see if I got something here. Let me pause this real quick. Alright, so the example was facing me right in the eye here. So what we got right here is chlorine, HH, chlorine, chlorine, and H. So these chlorines are very electronegative. There's more of them on this side. They're pulling the electrons towards themselves, and therefore they are de-shielding this proton right here. And looking at it, as we go further to the left, we're going downfield. This right here is going to be, and what do we say? Downfield is very de-shielded. Let's just double check. There you go. Downfield is very de-shielded. So as we go downfield, we're going to be with a proton or a hydrogen that is next to something very electronegative. Both of them are fairly downfield because we do have electronegative entities next to both of these hydrogens. But this one has 2 of them next to it. And if we look at it, this is a triplet. Alright, so my video got filled up, so I had to render it and delete some stuff, but here we go. We are talking about downfield and upfield. So as we go downfield, we are de-shielding, and this one is a triplet, therefore peaks minus 1 is 2 neighbors. We said that this one right here has 1, 2 neighbors, and hey look, it's next to 2 chlorines, very electronegative entities, therefore they're going to shift this downfield. This one, which has 1 neighbor, is just next to 1 chlorine, so they are not, it's still downfield, electronegative, but not as much as the 2 chlorine hydrogen. So let's do another example, like this one right here. We got HHH, we got H and Cl and Cl, and we got 2 extremes. This one's kind of more upfield, shielded. This one's downfield, de-shielded. The one that's de-shielded is going to be with the most electronegative entities, which is the 2 chlorines right here. And let's look, does it have 1, 2, 3 neighbors? Yes, it's a quartet. 4 minus 1 is 3 neighbors. And it's very de-shielded, so it's downfield. The one that's shielded is the one that's next, not next to anything electronegative, or at least directly next to it. And it has 1 neighbor because it's a doublet. 2 peaks minus 1 is, 1. And so it has 1 neighbor. So that is the downfield, upfield, de-shielded, shielded phenomenon. And I think that is it. I hope you enjoyed this video and it was a little helpful. Alright, have a good one.